Okay, on this video, we're going to talk about the projection, two important vectors, the projection of u onto v and the orthogonal of u onto v. And so what we're referring to here is if you have two vectors u and v, assuming they're not pointing in the same direction, and you line them up tail to tail, okay, the projection of u onto v, imagine the sun is out shining on a bright sunny day, u would cast a shadow on v. And it would be, we're assuming it's a right angle, that the sun is directly overhead. So the length of this vector, the length of the shadow of u onto v, is called the component of u onto v. That's the length of it. The vector itself is called the projection of u onto v. So that's the notation. So the component of u onto v is the magnitude of that projection. It's just the length of it. Okay. And then we could think of u then, we could write u as a vector parallel to v plus a vector that's perpendicular to v. Remember how we add vectors, the projection of u onto v plus, this would be called the orthogonal of u onto v, equals u. So u would equal the projection of u onto v plus the orthogonal of u onto v. So you can think of the projection of u onto v as the part of u that's in the same direction as v, and you can think of the orthogonal of u onto v as the part of u that's perpendicular to v. Okay, to find the projection of u onto v, we're going to first find the length, which is called the component. COMP is short for component of u onto v. That's the length of the projection. So using plain old trig, if I worked with this side, this length would be the adjacent side, and the hypotenuse is the magnitude of u. So the cosine of theta would have been the length, which is the component of u onto v, over the magnitude of u, adjacent over hypotenuse. So if I solve for the component of u onto v, I can multiply the magnitude of u over. So I get the magnitude of u times the cosine of theta. That's right here. So I just solve for this. Now notice I left a little blank there, and that's because the trick to figuring out the formula is that looks almost like the formula for the dot product. So if I multiply top and bottom by the magnitude of v, which is just like multiplying by 1, then the numerator turns into, by definition, u dotted with v, and then we still have this magnitude of v on the bottom. That's your formula for the component of u onto v. U dotted with v over the magnitude of v. Now the projection of u onto v, remember this is just the length of the projection. So the projection of u onto v would be this length, the component of u onto v, times the unit vector in the direction of v. Okay, so remember that's how one way we find vectors is you take a unit vector and then you multiply it by the appropriate length. So I prefer, okay, the book takes this formula and combines it with this formula, and you come up with an interesting formula, but it's hard to see the meaning behind the formula. So my preference, I have a separate formula for the component of u onto v. Once I find out what that is, then I'm just going to multiply it by the unit vector in the direction of v. So I don't like to use the formula that the book gives. Can if you want. Okay, and we'll do an example after we're done. Now, once we find the projection of u onto v, remember that from our picture above, the projection of u onto v plus the orthogonal of u onto v equals u. So if I wanted to solve for the orthogonal of u onto v, it would just be u minus the projection of u onto v. So there's 3 formulas. Okay, so here's an example. I've got 2 vectors, u equals I plus 3j. This works with 3-dimensional vectors as well, but we're just going to do it with 2 dimensions right now. And v is 5i plus 2j. So there's an angle between them, and the projection of u onto v would be the part of u that's going in the same direction as v, and the orthogonal would be the part of u that's perpendicular to v. So using my formulas for the component, it's just u dotted with v over the magnitude of v. Dot product is just 1 times 5 plus 3 times 2. And then remember, the magnitude is the square root of each component squared added together. So I'm getting 11 over root 29. The projection of u onto v is whatever that length is times a unit vector in the direction of v. So I'm going to take 11 over root 29 and times it by, not a dot product, but times it by v, which is 5i plus 2j divided by its magnitude, which is root 29. Now, if I distribute, the root 29s give me 29, so I'm going to have 55 over 29i plus 22 over 29j. That would be my projection. Finally, my orthogonal of u onto v is u minus the projection of u onto v. So I take my original vector u, subtract this projection. Got to do a little common denominator. Think of 1 as 29 over 29 minus 55 over 29 gives you negative 26 over 29. And if you do a common denominator for 3 and subtract 22 over 29, you get 65 over 29. Okay, now I thought it might be interesting. Why is this useful? This isn't the only example, but check this out. Suppose we wanted to find the distance from the point 1, 3 to the line y equals 2/5 x. We want to find the, and of course, whenever you find the distance from a point to a line, it's a perpendicular distance. Now, you've done this problem before. I know you can do this algebraically. I mean, think about the algebraic steps. If you wanted to find this distance, your first step, I guess, would be to find this point. And you could do that because we know the slope of this line is 2/5. A perpendicular line has a slope that's the opposite reciprocal. Once you find that slope, you could write the equation of the line going through this point with a slope of -5/2. Once you get the equation of that line, you can find the intersection of this line with this line to find that point. And once you find that point, you could use the distance formula. So you can tell it would be a lot of work algebraically to find the distance. But you may have noticed something, that picture is actually part of the picture we were just using. If you think of u as I plus 3j, that would take you to the point 1, 3. And v being 5i plus 2j would be like a line with a slope of 2/5, rise over run. So that distance we're looking for is actually just the magnitude of the orthogonal vector that we just found. We just found that up. I'm going to slide this down, up. We found the orthogonal vector here. It's just going to be the magnitude of that vector. So you can do the square root of each part squared. I didn't work it out, but I know you could do that. And so you can see with vectors, when you have a little understanding of how they work, some of these difficult algebra problems trying to find the distance from a point to a line can be made a little bit simpler, I think, than doing it algebraically. So that's one application of understanding how to find a projection and an orthogonal vector.